Hi, my name is Zhe. I'm a PhD student at the University of Manchester, and this video presents our paper, Self-organized flocking with simulated homogeneous robotic swarm. Flocking is a common behavior observed in social animals, such as birds, bats, fish, wild beasts, and insects. Inspired by these collective motions, swarm robotics was proposed as a research topic, which provides collective strategy for a large number of simple robots to achieve collective behavior. Swarm robotics potentially provide promising solutions to some problems in several areas, such as balancing the exploration of renewable resources, photo detection, collective mapping, collective sensing, pollution source localization, cleanup. You can even imagine it might help us to identify people and animals trapped in a bushfire. I'm interested in creating this kind of collective motions. You can see how the flocking robots collectively move to a target direction on the bottom side of this slice. In this paper, we identified and proposed solution to the current gap between theoretical model and the implementation with real-world robots. Also, we provide guidance on the application with real robots in terms of factors and strategic design. In homogeneous swarm, every individual follows the same strategy to achieve a common task. Hence, there are no behavioral or physical difference between the individuals in the swarm. Much of this research focuses on active elastic sheep model, namely AES model, which is a self-proposed mechanism where swarm particles can successfully achieve collective motions. The AES model was originally developed and investigates using particles. To make it feasible for swarm robots, we developed a method and used this model with considering the hardware strategy of physical robots. Let's see how AES work. There are two constraints for each robot, the position, PI, and rotation, phi. The movement of each robot is controlled by two different forces, the go forces Fg and the collective force Fi. The go force aims to steer the entire group move toward a desired direction, while the collective force is used to keep robots within an expected distance to avoid the collision. The coefficients alpha and beta here are related to linear speed and rotation of the collective motion. Ni, perp are unique vectors, where Ni has the same direction as the heading of the robot, and in the picture it will be along the y-axis. Well, the Ni perp is perpendicular to the heading direction, and in this picture it will be along the x-axis. Dr is a noise value in the process of detecting distance between robots. And the gamma R is a unit vector with a random direction, so that noise is applied in an arbitrary direction. The phi I, the angle which the robot eye is expected to rotation. The clockwise direction is defined as positive, and the counterclockwise is negative for phi I. CD and CP here. These are corresponding weight coefficients of go force. Vi is related to the desired group velocity along the self-propulsive direction, which is proportional to the go force. So you can see the FDG relied on the distance between the robot location and the goal D. The goal force FGP is related to the desired group force, group speed Vi. The movement of each robot is controlled by two forces, and the collective force Fi is used to keep robots within an expected distance to avoid collision, and the goal force aims to steer the entire group move toward the desired direction. As you may notice, the goal force Fg is constants of FGD and FGP, and each individual robot gets information about surrounding robots using the sensors. The summation of sensor value is presented as a collective force Fi, as shown in the last formula. For more details on this specific constraint, please take a look at our paper. In terms of the experiment, we use Epoch as the robot and Weebot as a simulation environment. As you can see in the first picture, in order to test a group's behavior with different kind of initial situation, the start orientation of each agent was randomly set between -pi to pi. And in this work, local communication relies on sensor values to make sure that the robots make desired distance from their neighbors. Each robot only detects the distance to its neighbor without acquiring the neighbor's identification. So each robot is able to make decisions without an extra observer and the whole process. Since the model of each individual robot includes all the physical properties, which are carefully implemented by the control algorithm, the study here can be considered as a first step from an obstacle model to the progression with real robots. And the final picture is a screenshot which shows the group of robots move to a desired direction. For the flocking method, every robot has a controller to collect and calculate their own data. The data is generated when every robot detects neighbors using sensors, which is also for calculation of collective force Fi. In every individual controller, total force is calculated based on Fg and Fi using the AES model. After obtaining the force information, the controller starts to calculate total force and correspondingly change the robot's kinematics. After the experiment, we had the we design a matrix to evaluate the likelihood of individuals remaining in the group. Here, the average distance within the flock was chosen to show the coherency of the swarm. The average distance in this paper means the mean value of the distance between robots, which can be calculated as this formula. As you can see, the RIG is the distance between robot I and robot J, and N is the number of the robots in the group. Experiments were designed with different factors, which are swarm population size, desired distance between robots, and the goal force. In this experiment, only the object factors is an independent variable, and other factors are fixed. Box plots were used to show the distribution of metrics. As you can see in this slide, the impact of population to the average distance. As shown in the first picture, distribution of obtained results increase over time. Hence, it's evident that since it's evident that the maximum DS increase, namely DS have a greater chance to reach the maximum value of a test at the end of the experiment. The minimum and maximum DS also see decrease as the population increase. It can be clearly observed that the medium DS decrease as population increases as well. The swarm with a larger population have better group performance when other factors are the same. In terms of the goal force, the impact of the goal force, the bigger force triggers larger DS, resulting in worse coherency regard of the population size. A bigger desired distance leads to a larger DS for small population size, such as the population sizes 4 and 6. In constraint, bigger desired distance contributes to smaller DS when the swarm has a larger population size. Now let's compare these factors. And we use analysis of variance tests to show the impact of different factors. The number of robots play the most significant role in the coherence because the p-value of the population size is far less than 0.5, almost equal to 0, which is quite small. So when we increase the population size, contribute to better group performance significantly. Though desired distance has an impact on the coherency of the swarm, the influence is less than the population size and force. The force has a less impact on coherency with p equal to 0.691. So compared with a swarm with fewer robots, large-size robots tend to have more coherent performance even under different goal forces and desired distance. This information will potentially help follow-up studies to address several questions of implementation using real swarm robots in real-world application. These are the media sources I've used in this presentation. Thanks for watching.
Ladies and gentlemen, hello everybody. My name is Shi Wang from Swarm and Computational Intelligence Lab. We are a member from the Department of EEE at the University of Manchester in the United Kingdom. I appreciate the opportunity to present our work about investigation of queue-based aggregation behavior in complex environments. If you have interest in our work, please visit our website www.swacil.com for the latest update. This is the outline of my presentation today. First of all, I would like to talk about swarm behaviors, especially aggregation, including the algorithm BigClust. After that, I'm glad to introduce the simulation platform which developed by ourselves, BigGround. I will also mention the model we used in this paper. After that, I will choose some important results which generated from the experiments, and finally, I would like to make a conclusion and talk about our future work. Aggregation is a common behavior observed in different species in nature. In aggregation, individuals gather in one area with or without an environmental cue. Aggregation is the basic and prerequisite for many complex swarm tasks. There are two types of aggregation behavior in nature: queue-based aggregation and self-organized aggregation. In queue-based aggregation, there is a queue present in the environment where animals gather. The queue represents the optimal location in terms of temperature, humidity, or such. Hence, in queue-based aggregation, environment plays a very important role, and in most cases, the environment is very complex, have multiple queues, obstacles. This makes aggregation a very challenging task. In self-organized aggregation, there is no queue in the environment. Animals gather in randomly location without a particular external cue in the environment. Researchers in swarm robots study aggregation behavior in nature to replicate it artificially with robots, since aggregation behavior is the basics of most of the behaviors in swarm robotics. Among different approaches, BigClust algorithm that mimics the behavior of honeybees is one of the simple yet a very elegant approach to queue-based aggregation in swarm robots. A robot moves forward continuously in the environment. When it encounters an object, it checks whether the object is an obstacle or another robot. If it is an obstacle, the robot avoids the obstacle and continuously to move forward. If not, it stops and waits for a particular amount of time. Most of the previous studies, which are based on real robot implementations, use small swarm populations, and the duration of the experiments was very limited. There are relatively few studies on the aggregation of swarm robots in a complex environment with multiple queues and obstacles. In this paper, we studied the aggregation of large number of robots using BigClust algorithm in an environment with two queues having different intensities and an obstacle. We investigated the effects of environmental factors on the aggregation. The robotic validation of BigClust strategy in a complex environment is the main motivation of this paper. We developed a simulation platform, we call it BigGround, on Unity real-time development platform. BigGround is able to simulate long-term operations of swarm robots in various complex and dynamic environments, including obstacles and multiple sources. Experimental configuration. We implement aggregation with two different cities without an obstacle and with variable size obstacles. Firstly, the arena size was 440 cm in length and 200 cm in width. It was surrounded by walls. An obstacle with different lengths was set up in the middle of the arena between the two sources. Two grounded bases heat sources was set as queues in this study. The one on the left side, we call it local optimal, had a temperature of 125 units out of 255 at the center point with a radius of 40 cm. The heat source on the right hand side was global optimal. It had a temperature of 255 units at the center point with a radius of 60 cm. All the robots were randomly placed on the left side of the arena to keep them away from the global optimal. They move according to the Big-Closed algorithm during the simulations. Each simulation lasted for 3,600 seconds and all the experiments were repeated 20 times. This is the model for aggregation behavior in this study. We call it stock flow model. For detail, please check our paper. I would like to choose some important results. This is the results for the part without obstacles. In the first figure, illustrate the aggregation size on the mean queue from experiments without obstacle. The 5 simulation showed a similar trend. The number of robots in the mean aggregation increased a stable value. Monotonically increased the number of the robots, increased the size of aggregation. However, there was a significant difference in the time they reached the final number of aggregations. The group of 300 robots took about 910 seconds to reach 70% of the final aggregation size on the mean queue. Meanwhile, the group of 100 robots took only about 400 seconds to reach 70% of the final aggregation size. It is not so obvious, but however, it was mentioned that the ratio at which the final aggregation size to the total number of robots increased slightly as the number of robots increased. The middle figure shows the observed aggregation size on the mean queue during experiments with different population size. Also, the value from our model was showed the gray color dashed lines. The right figure illustrates the size of aggregation on the small queue on the left hand side during 3,600 seconds. The results revealed that the situation in the local optimal source was more complex. In the beginning, the number of robots aggregated in this area reached a peak and then fell back to a stable value. There was a proportional relationship between the aggregation size and the number of robots in the first half time of the experiment. However, as the size of aggregation stabilized, this proportional relationship became less obvious. The observed results showed that in the simulation of 200 to 300 robots, the final size of aggregation were almost the same. There was also no significant difference between 100 and 150 robots. Each group of our simulations showed that the global optimal source could eventually attract more robots to aggregate it than the local optimal source. Although the capability of BCLUST in finding the global optimal was demonstrated, the speed and efficiency of completing the aggregation were different. The total number of robots affected the aggregation speed in the global optimal source. The larger the number of robots, the slower the gathering speed of the robots. It is due to increase in number of inter-robot collisions. This is the results about the experiments with obstacles. The left two figures shows the experiments of a robot size of 200 robots, and the right two figures shows the results of 300 robots. The first figure illustrates that the size of aggregation size with 200 robots in experiment with different obstacle size. The gray dotted line shows the aggregation result in a no obstacle environment. In the global optimal source, we found that the size of obstacle affects the aggregation time. The larger the obstacle, the longer it took the robots to aggregate it. In the arena divided by obstacles with about 36% and 60% of the arena wise, the final aggregation size reached a stable value that was almost the same as that in the no obstacle arena. In the arenas divided by 84% and 92 obstacles, the aggregation size increased very slowly and did not reach a stable value. The second figure shows the aggregation size during 3,600 seconds on the left queue. It was found that the size of the obstacle affected the peak value of the aggregation size. Hence, in the experiments with obstacles of 92% of arena-wise, the numbers of aggregated robots was close to the maximum number of robots that could be aggregated in this area. Aggregation size and obstacle length had an inverse relationship, which the number of aggregation robots decreased as the obstacle size increased. In the arena divided by the obstacle with 36% and 60% of the arena wise, the final aggregation size was the same as in the no obstacle arena. However, the experiments with longer obstacle, 84% and 92% of the arena wise, a stable value in the 200 robots experiments was doubled and trebled as others. The right two figures shows the similar situation for 300 robots. However, in two extremely difficult situations, the obstacle length of 84% and 92% of the arena wise, we did not expect the robots can successfully aggregated at the global optimal source during the experiments. Therefore, we just calculate the ratio in which robots overcame the obstacles. In experiment with 200 robots, 44.5% robots, that means about 89 of 200 robots overcame the obstacle at 84% of the arena wise. Meanwhile, the ratio in case of 300 robots is only 39.7%. The similar situation observed in the experiments with obstacles in 92 of the arena wise in both groups. The ratio were 19% and 14.3%. It is shown that the length of the obstacles influence the aggregation speed and ratio in the global optimal source on the right-hand side. The larger the obstacle, the slower the aggregation speed of the robot. It also affects the peak value of the number of aggregated robots in the local optimal on the left-hand side. It was unexpected that the presence of obstacle under certain circumstances had a positive impact on the aggregation size. For example, for 200 robot situation, the final aggregation performed in small obstacle experiments, 36% or 70% were better than those without obstacles. Our view is that the obstacle reduced the possibility for free robots on the right-hand side to leave the area. On the other side, the number of robots was not always a positive factor for aggregation. In experiments with 84% and 92 obstacle, the group with 300 robots performed worse than the one with 200 robots. The observed behavior showed that the higher the number of robots in the arena, the fewer the number of robots that can cross the passages made by the long obstacles. We observed the different stage of experiment and found that the robots continually hovered near the passage, thereby reducing the possibility for other robots crossing the obstacle. The results showed that although the big groups algorithm is a simple system, but it was a successful algorithm in contouring a large swarm in complex environment. The results demonstrated the feasibility of the aggregation in finding the global optimal source in presence of multiple sources. It was illustrated that the robots could overcome a certain degree of environmental complexity thanks to the robustness of swarm systems. Meanwhile, in a complex environment with limited access, the swarm population was not always a positive factor to the final aggregation size at the global optimal source. And the simulation platform BigGround is efficiency, flexible, and realistic platform for the simulation of swarm robots scenarios. It is an open source platform on GitHub. This platform is stable and for simulating more complicated environments such as continuously changing environment and multiple queues. We are still improving our simulation platform BigGround. Now we can do more simulation for different scenarios such as static and dynamic environment. We also try to add some machine learning features in BigGround. So this is our presentation today. Thank you for your attention.
I'm Fu Xiaozhou from Shanghai Jiaotong University, Shanghai, China. Today, I'm going to give a presentation of my paper, a tamper-resistant and decentralized service for cloud storage based on layered blockchain. First of all, I'm going to introduce backgrounds. Nowadays, data is becoming more and more substantial, and the network resources becoming more and more scarce, and centralized services have encountered performance bottleneck. Existing solutions to solve this situation is edge computing and fog computing. So ensuring data integrity and validity is essential in edge scenarios. In this paper, our goals are to propose a decentralized cloud storage service secured from tampering and develop a decentralized service based on blockchain for cloud storage. In this paper, we develop a decentralized service based on blockchain for cloud storage to supply users with a tamper-resistant function. This service can manage and preserve the meta information, and also can position, check, and verify the meta information. To cross the barrier of capacity limit and scalability, we come up with a layered and collaborative structure. In our design, the main chain stores indexes of metadata, while subchains allow users to upload metadata and digest of source data. In this paper, we have made three contributions. The first one is to propose a simple storage strategy to relieve the contradiction between huge data volume and limited network resources of the cloud. The second one is to propose a design of decentralized cloud storage service based on blockchain, which provides powerful tamper resistance and access. And the third one is to propose a layered structure design of blockchain to expand the storage capacity without sacrificing scalability. This paper implements our ideas as a form of cloud service, collaborating with outer storage systems. Our service is capable of providing reliable functions to users. The figure below demonstrates the service architecture. The layered design of the blockchain network increases the storage capacity and enhances scalability. Subchains can be added in any position according to actual demand. Although the traditional blockchain provides a strong guarantee for security, it cannot fully meet our requirements for two reasons. The first reason is the capacity limit, and the second reason is the scalability defect of blockchain. Because of the considerations above, we designed a two-layer structure for our blockchain network. There is a main chain and several subchains in our network. In the data storage service, we designed a unified data structure to store metadata and digest of source data in subchains. As shown in the first figure, we use 6 parameters to represent specific information. As shown in the second figure, we design another unified data structure to store indexes of metadata in the main chain. There are 3 interfaces in data storage service. Put S is used to insert records into subchains. Put M is usually called after put S to upload the UUID and the subchain ID to the main chain, and remove is designed for deleting records in subchains. Different from the data storage service, the data query service does not interact directly with subchains. The interface exposed by the data query service is shown in this slide. Between the 2 parameters accepted by GET method, UUID is optional. With both key and UUID, the result returned will be a pair of metadata and digest. The implementation of the access management service is based on the 2 parameters in records that are stored in subchains. They are reader set and writer set. Records can only be accessed by users in their reader set, and users in the writer set own the permission to modify parameters except for UUID and metadata in a record. The read flow can be divided into 5 steps as shown in this slide. In the read workflow, users do not interact directly with subchains. The reason is that subchains are usually composed of relatively few nodes, consequently more vulnerable. This design can effectively isolate errors, even if some subchains failed. The biggest loss is just missing some data. The right flows are shown in this slide. In the right workflow, choosing a subchain is a key point. For taking up less bandwidth and lower latency, the nearest one should be selected. Our service is designed specifically for the cloud environment. The main chain nodes should be deployed closer to the cloud center to cover a larger range. Nodes of subchains should be adjacent to the outer storage system, which are deployed in edge nodes. However, nodes of the special subchain designed for the access management service called AM subchain node should to be neighbors of the main chain nodes for lower latency. This paper measured the latency of read operations, as shown in the left figure, with a different number of records inserted from 1,000 to 40,000. The read latency keeps around 5.6 milliseconds, and the size of records may also affect the read latency. We inserted records with different value size before starting the reading test, and the result is shown in the right figure. Then, this paper measured the latency of write operations, as shown in the left figure, with a different number of records inserted from 1,000 to 40,000. The read latency keeps around 60 milliseconds. We inserted records with different value size before starting the writing test, and the result is shown to the right figure. We can see from the result that both for performance and capacity considerations, the size of the digest uploaded by users should be limited to under 10 KB. In this paper, we built a system with a main chain and two subchains. The main chain has 4 nodes, while each subchain has 3 nodes. The table below lists the probability of each chain being inaccessible when a certain number of arbitrary nodes have crashed. And we can see that the blockchain network has high availability, and adding more nodes will greatly enhance it. The above is my presentation. Thanks for listening. If you need more detailed content, you can read my paper. And if you are interested in this research, you can contact me. Thanks.
Okay, welcome to our presentation today. And this presentation is for a conference that we were hoping to attend this year. And obviously, due to COVID, we will be unable to present this paper in person. And in light of that, we're giving a video presentation. The workshop SITN is based on blockchain and blockchain related research. And so this talk that we'll be giving today is for that workshop, and we'll focus on a blockchain-based cloud-integrated Internet of Things architecture using a hybrid design. And this workshop was to be held in conjunction with CollaborateCom or CollaborateCom 2020, which was supposed to be in Shanghai in October. And in light of that, we're presenting this online. I'd like to thank the organizing chair of the conference, Zion Tan from the UK, and also Mian Jan from Pakistan, Wei Zimeng and Zheng Kang Li from Denmark and England, respectively, for holding this workshop and allowing us to present our research. So this paper, a blockchain-based cloud-integrated IoT system using hybrid design, is joint collaborative work between myself, speaking right now, Gautam Srivastava, and some colleagues in India, Rupa, who is at the VR Siddharth Engineering College, and Praveen, Tippa, and Sweta, who are longtime collaborators of mine based at Vellore Institute of Technology in Tamil Nadu, India. And so our paper, just to give you a brief outline of what we'll be talking about today, we'll start with discussing the overview of the paper, get into some related work, and look at some of the limitations in current cloud infrastructures. And then we'll talk a little bit about our proposed architecture, and then go into some modules that we've created, and then talk about concluding remarks and future work that we'd like to undertake. And so to kind of summarize what this paper was about or is about, we can say something along the lines of that in highly confidential areas like military bases, UAVs, so basically drones, other types of vehicular items, are basically artifacts that can travel in the air. And so what we want to talk about with this research is basically looking at unmanned aerial vehicles and that can monitor and provide services in areas that may be unsafe for humans or for the users of these drones. And so even in many industrial areas, UAVs can be used to monitor places easily and in a controlled manner. And so when we're using these unmanned aerial vehicles, privacy preservation of the data that's being used by these UAVs is a primary concern. So, I mean, you can take examples where UAVs are taking video or basically collecting data with sensors. And so that information may have some privacy connotations involved with it. And so since these UAVs to move data around basically in any sort of an IoT setting would be using cloud for storage of the data, because most of these UAVs have limited storage. And so we need to be able to think about ways that we can protect the data that's flowing between the UAV, the cloud, other devices. And so what we're proposing here is basically a hybrid design using cloud infrastructure and blockchain to basically, through voice commands or buttons or accelerometers, be able to create security features for the data with some flexibility involved as well. And so in Anthe et al. one of our references here, they proposed a 3-layer intrusion detection system to defend IoT devices. And so the main functions in this system, in this paper, were classification of device behavior, identification of suspected packets, and classifying the attack. So, I mean, it was a nice paper or group of papers that basically looked at these intrusion detection systems and were able to use network traffic to try to identify malicious packets, and then basically as well try to classify what types of attacks were coming from previous knowledge. And so some of the drawbacks in this paper were that anyone could easily modify or update the data. And so this could cause problems because if someone could modify the data that's coming in, they may be able to thwart basically the attempts to find these attacks. The man-in-the-middle attack was a major downside of this paper. It was still something that was left unsolved. And it was not possible to operate at any time in any place these sorts of infrastructures. So they needed high computational power to run the attack defense mechanisms. And so even though it was a standalone system, just the amount of power, basically computational cost that was involved may not make this feasible, say out in the field or something like that. In another paper by Arshad et al., they proposed an intrusion detection system using Internet of Things infrastructure. They were able to address some of the open challenges that were left unsolved in the previous paper. But what they had as far as lacking in their work was there was a lack of security, and still the man-in-the-middle attack was still able to be something that was of danger to this system, and there was also no proper mechanism to preserve the data. And so what we can see in the different related works, and these numbers coincide to basically papers, or the papers in our work here, is that there wasn't, first of all, not a lot of them were blockchain based, so that's a major difference between what we were proposing. Another thing was that very few of them had full transparency and were mobile, could be used in the field. And so looking at some of the previous works and comparing to our work, we were able to achieve what we would consider more of a usable infrastructure that could be used in an IoT setting out in the field or somewhere remotely. And, getting away from that centralized system using the cloud is definitely a plus point as well to our system. And so in our proposed architecture, we use a hybrid design based on virtual circuit-based surveillance that can be controlled and maintained by the following operations. We have Blink applications. So basically using blinks, we can control the system. We have Google Assistant for that. We also can use mobile tilting sliders in cloud and different basically operations to make that happen. And so when we're talking about the system processes, what we were able to do, and I'll show you this kind of in a diagram next, is basically using a MCU unit and Arduino, motor drivers, wheels and camera, and required vehicle components. We're able to deploy our system for testing, writing most of our code in Python. And so basically the user can give instructions to the vehicle through mobile devices, and the instructions then are passed through it through different commands. So what you can see here is that, so over here, what you're looking at here is basically our system, and basically being able to use the camera and any sort of Blink application on the gateway. We were able to achieve our architecture that was able to move any sort of UAV through a mobile device, or something, any sort of IoT device. And so once we start monitoring the surroundings with the camera, simultaneously the captured data is compared with the registered data. Okay, and so if any intruder is detected, the data will be stored in the cloud as well as in the blockchain through the gateway. So by having an active intrusion detection mechanism, we're able to protect the data in real time. And so that's a big plus point to our system and something that we were able to achieve through blockchain. So our system itself consists of 3 modules, and that basically operate simultaneously. And those 3 modules are the design development of a virtual circuit based on IoT, the deploying of data in a cloud environment, and the deploying of data in the blockchain environment. And so in a standard sort of blockchain image that we've seen, in lots of papers, what you're seeing here is basically the user can request the mobile device um, about some sort of action. And so then the mobile device will request the system, and the system, based on using the cloud and blockchain, will be able to store data that is captured, and also make sure that data gets verified, or transactional data gets verified, using the blockchain as well. And so we have a system here. I mean, this diagram here, we've seen similar diagrams in many blockchain papers, basically how we would fit in the blockchain into this infrastructure. So here what we're basically seeing is twofold. Data is secured, stored on the cloud, and simultaneously the transaction of the data gets stored on the blockchain. And so those blockchains then become our mechanism for verifying, or basically validating, the data that we stored on the cloud for any sort of data that's captured by UAVs. Okay, and then there's a few algorithms here. Basically, I mean, you can look at this stuff in the paper as well, just so I don't run out of time. But there's algorithms for our 3 modules that we talk about here. Okay, so 1, 2, and 3. These 3 modules, there's 3 algorithms involved that you can look at the details and read about them in the paper. And so remember, like with blockchain, I mean, we don't want to store a lot of information. Our transactions need to be somewhat compact. And so, we're basically want to use the blockchain to validate data that was stored on the cloud. And so that becomes the main point there. And so in conclusion, basically, and you'll see from the paper and the extended version that should be out probably in 2021, that we were able to carry out extensive experimental analysis on our system to show both its security and its efficiency and its ability to be basically run remotely. And so, in conclusion, for the paper from the workshop, what I'd like to say is that the proposed system, the hybrid system that uses both cloud and blockchain, is able to improve certain factors of data privacy and portability. Data privacy can be achieved here not only by storing the data on the cloud, but when data is stored on the cloud, a transaction of the data that's stored on the cloud is registered on the blockchain. And so that becomes something that we're able to verify at a later date using some of the blockchain characteristics like immutability, etc. We can make sure that data then, once it's on the cloud, if it's changed at some point, I mean, we should be able to detect that using, a hash. And so now we've created a system adding in the blockchain that no one is able to modify or delete data without the system recognizing that that's happened. And that's huge. And so our proposed system in this paper can be used to monitor and record illegal activities, and that becomes a very important task in today's world. As far as future work goes, okay, we want to be able to design the proposed system using IoT components, and what that'll end up looking like is being able to create one of these IoT systems to test this on full bore. And so in our journal version of the paper, our extended version, we'll see some of that come into fruition as well. And at the same time as being able to test our system for efficiency, we want to be able to test it fully for security and make sure that it outdoes some of its competition or basically previous papers in the sense of, man in the middle attack. Are we secure from that? And other known attacks, we want to make sure we're secure from that as well. So just some references just to end the paper. Okay, we've talked about some of the papers here, and you'll see if I go back to this slide, I mean, some of the main numbers: 7, 15, 7, 15, 21, 29, and 36. These were the main previous works, and so you can pick them up here in these slides here. So 7 is here. Sorry, let me get out my draw tool. Okay, we have 7 is here. 15 is here. These papers. So these were, the main previous works about intrusion detection. And then we also have 21, 25, and 36. 36 is on the next page. So these are the ones I'd probably focus on more so. .36. Okay, and those were the main previous works to this one. So unfortunately, obviously, we weren't able to meet in person for this talk. If you have any questions, I can take those either via email or I'm not sure what the format of this is going to be for questions, but feel free to email me if you want to discuss the work further or you want to collaborate on future work to do with this project. So as authors, we'd love to hear from you. So thank you. I hope you enjoy the rest of your the conference and the session. This was for the SITN workshop that was part of CollaborateCom 2020, and the SITN workshop focused on securing IoT networks. So different mechanisms for doing that, and blockchain nowadays, as far as Internet of Things research for security, is one of the main focal points. What we should see in the future also is a lot more papers on federated learning for security and how well that fits into IoT networks. So I look forward to seeing more papers in that direction as well. Okay, so thank you for your time, and hope to see you soon.
Good morning. I'm Yilei Zhang from Anhui Normal University and the Chinese University of Hong Kong. Today I will present our work towards efficient and privacy-preserving service QoS prediction with federated learning. In this presentation, I will first give some introductions about the service QoS prediction problem. Then we will discuss several challenges we are facing about the efficiency and the privacy issues. In the third part, I will give the efficient and privacy-preserving QoS prediction approach proposed in our paper. After that, we conduct several experiments and I will show the experimental results. Finally, we will conclude this paper. Cloud computing provides many service resources. With these services, large-scale cloud applications can be built and adopted in many critical domains. These cloud applications provide services to millions of customers around the world on a 24/7 basis. With the rapid growth of service market, a large number of services are publicly accessible in cloud to provide various atomic functions, which makes service-oriented architecture has become the primary paradigm for constructing cloud applications. Desired services are discovered and composed by users in a loosely coupled way at both design time and runtime. For example, in the website Priceline, it provides various vacation packages to their customers. For a specific user query, the website needs to invoke remote services for the information about hotels, flights, cars, etc. Ensuring the performance of cloud applications, especially those used in key areas such as government, healthcare, and finance, is a big challenge, as it is difficult to get details of the internal implementation of services provided by third parties. Therefore, in order to ensure the performance of cloud applications, it is very necessary to select high-quality services. In the cloud, there are many functional equivalent or similar services. For example, in this picture, there are 3 car rental services provided by different companies. Therefore, to ensure the performance of a cloud application, how to select high-quality services becomes a very important research problem. Generally, effective service selection employs QoS as a primary indicator to distinguish a set of candidate services with equivalent or similar functions. QoS is widely used to describe the non-functional characters of services, such as response time, throughput, availability, etc. The QoS values of services hosted by different providers may vary depending on the server-side environment, such as workload, bandwidth, and also will be affected by the user-side factors like device capacity, location, or the network environments between users and the services. The observed QoS for each user is different from others, even on the same service. That is, different users may observe personalized QoS values. Therefore, effective service selection is highly dependent on the user-perceived QoS values of services. However, it is very difficult to get QoS values for all candidate services, because each user invokes only a very limited number of services and can only observe the QoS values for the corresponding services. It is also impractical to actively evaluate these QoS values due to the high cost of invoking a large number of services. In recent literature, QoS prediction has been proposed as a promising approach for estimating the unknown QoS values. Collaborative filtering is commonly employed by QoS prediction approaches to solve the QoS prediction problem. As shown in this picture, each cloud application keeps their QoS records locally, and then the application will send the QoS records to a central server. A global QoS dataset is formed by collecting user-contributed local service records. By building a prediction model on the dataset, unknown QoS values can be estimated by the model rather than measured by actual invocations. Then the prediction results will be sent to each cloud application. Then the application will use these prediction results to help select high-quality services. This figure illustrates a toy example of matrix federation in QoS prediction problem. As shown in this figure, the invocation from a user to a service is represented by a solid line. The user records the QoS value it observed in the QoS matrix in the corresponding entry of the invocation. In the matrix, each row represents a user, each column represents a service, and each entry represents the QoS value of the corresponding service observed by a user. An empty entry indicates that the corresponding user did not invoke the service before. By decomposing the matrix, users and services are mapped into a low-dimensional joint latent factor space, so that the existing entries in the QoS matrix can be recaptured as the inner product of the latent vectors in the space. Finally, the unknown entries in the matrix can be predicted in a similar way using latent vectors as shown in this figure. The model can be formalized to minimize the following loss function. The first term calculates the sum of squared errors between observed QoS values and the predicted ones. The last two regularization terms is used to avoid overfitting. Unfortunately, the practical use of the matrix federation is severely hampered by privacy issue. In order to receive the predicted QoS value from the prediction model, users need to provide their local usage data, which may disclose their sensitive data and privacy. It is difficult for users to prevent others from inferring personal information or reselling their data. Consequently, some users are concerned that their valuable data may be leaked and will not participate in the collaborative modeling. As a result, the limited historic training data leads to low prediction accuracy of the model. In recent literature, there are some data conversion techniques employed by the privacy-preserving QoS prediction approaches. These techniques include encryption, obfuscation, and other data conversion techniques. While these techniques can provide a certain degree of privacy protection, they still face the following limitations. First, all users need to transfer their local usage data to the central server. Large-scale online applications typically run around the clock and support millions of customers, generating an incredible amount of usage data. Transferring large amount of data over the network imposes a huge overhead on users and the central server. The use of obfuscated data techniques can lead to the loss of some useful information on the original QoS data, which will affect the accuracy of the model. It is also very difficult to determine the level of obfuscation to balance the trade-off between privacy preservation, and prediction accuracy. Due to the large amount of data needed to train the predictive model, it puts forward an extremely high demand on the processing capacity of the server. It is a very, very huge challenge for the central server to provide prediction results to all users in a timely manner at runtime. In addition, the data encryption and data decryption also need the central server to spend some time to process this data. Therefore, in this paper, we propose an efficient and privacy-preserving QoS prediction approach. We aim to solve the following two research problems. The first is how to protect user privacy while enabling collaborative QoS prediction. The second problem is how to provide prediction results efficiently at runtime. The first step of our approach is to conduct data transformation. As shown in the figure, the distribution of response time and throughput values in real-world QoS dataset have high skewness and large variance, which is conflict with the probabilistic hypothesis of matrix federation. So we conduct box-Cox transformation, and the right two figures shows the data distribution closer to normal shape after data transformation. This figure illustrates the federated QoS prediction framework. Users record the observed QoS data locally while the application is running, and this data does not need to be transmitted to the central server. Part of the matrix federation process takes place locally at the user side and is integrated again at the central server through federated learning technologies. Each user simply sends the update local service prediction model to the central server and keeps the raw QoS data and the user local model at the local side. Then the central server collects the updates from all users and combines them to determine the updates that should be made to the global model, and then provide the updated model to all users in the next round. Each user can quickly predict unknown QoS values using local model and the global model. In order to prevent the central server from inferring user privacy from gradients, we adopt differential privacy technology to encrypt and decrypt gradient parameters transmitted between the user and the server. There are 4 steps. The first step, we add some noise to the gradients. Then we encrypt the gradients and transform it to the central server. Then a global aggregation is performed at the central server. After that, the central server can decrypt unbiased estimate of the global aggregation and update the global model. While federated QoS prediction approaches can protect user privacy, further improvements are needed to accommodate the diversity capacity of user devices. As cloud applications usually run on customers' devices, such as desktops, laptops, tablets, smartphones, and in-car systems, computing capacity and network bandwidth may become bottlenecks. In order to solve this problem, we propose several techniques to improve the model efficiency from 3 aspects. The first is we try to reduce the overhead of user-side computation in each round. We use optimized initialization, and we only process newly observed QoS data through SGD techniques. The second aspect is to reduce the size of transmitted message in each round. We choose to transmit the updated subset of the gradients, and we also choose a random subset of the gradients. After that, we also have proposed a technique to compress the transmitted data. The third aspect is to reduce the number of communication rounds. We set an update threshold to help reduce the number of communication rounds we needed. We conduct experiments on a commonly used real-world dataset to evaluate the QoS prediction approaches. This dataset contains two important QoS attributes, response time and throughput. We can also easily extend our approach to other QoS attributes. And this table shows the statistics of the QoS dataset. There are 142 users invoking more than 4,000 services and 64 consecutive time slices, and each slice for 15 minutes. We use MAE as the evaluation metrics. We compare our approaches with baselines and counterpart approaches. UIPCC and PMF are classical QoS prediction approaches. PPMF, considering the privacy issue. FMF are proposed in this paper. It is the federated QoS prediction approach. EFMF further extends the FMF approach with efficiency improvement technologies. The results show that FMF and EFMF have higher accuracy than UIPCC and PPMF. The prediction accuracy of our two approaches is similar to that of PMF. However, PMF does not consider privacy issues. The experimental results show that the proposed privacy-preserving QoS prediction approaches are effective. We also compare the convergence time of different approaches to evaluate the efficiency. And these two figures show that EFMF needs less time than other approaches to make prediction. Since the federated QoS prediction model is trained in a distributed manner, it includes both local models and global models. We further analyze the scalability of our approach. We compare the median convergence time and the different data volumes by varying the number of users and services. The results show that EFMF can be easily extended to process large-scale data from more users and services than other approaches. In summary, we propose an efficient and privacy-preserving QoS prediction approach in this paper concerning two issues, privacy and efficiency. We propose several key techniques including data transformation, federated matrix federation, differential privacy, and efficient federated learning technologies. The experimental results on a large-scale real-world QoS dataset demonstrate that our approach is effective and efficient while effectively preventing privacy threats. For more details, please refer to our paper. If you have any question, please kindly drop me an email. Thank you.
everyone, this is Ming Xian from Shenzhen Institute of Advanced Technology, Chinese Academy of Sciences. Today I will bring a topic about a reinforcement learning-based approach to identify resource bottlenecks for multiple services interactions in cloud computing environments. This research work is a joint work between the industry and the universities and the research institutes. Including the Siemens Industry Software of Chengdu in Chengdu and the University of Electronic Science and Technology of China, University of Victoria, University of Melbourne. In today's talk, I will firstly introduce the background of this research. Then I will discuss about the system model and the problem definition, including the system view and the modeling. Afterwards, I will discuss about the proposed approach, which is a policy gradient-based reinforcement learning approach. Then I will show the evaluations of our proposed approach, and finally, the conclusions and the future work will be given. Okay. Firstly, I will introduce the background of this research topic. It's about the resource bottlenecks in clouds. So in cloud environment, different customers can use different services, and the service provider would like to set up their services and charge the revenue profits from the customers. So from the service provider's perspective, they need to estimate how much of the resources will be used, thus they can optimize the resource usage and improve their profits. However, the bottlenecks can greatly affect the performance and the user experience. For example, different cloud services often provision various resource capacity, and these bottlenecks of individual services are more difficult to be predicted. So this diagram is derived from the Siemens scenario. The left component is the load generator, which will generate loads for the Siemens system. The Siemens services are deployed on the public clouds, such as like the Alibaba Cloud or the Google Cloud. And there are multiple services which are interacting with each other in this scenario, including the service load balancing gateway, the gateway based on the Kubernetes service, and some non-functional requirement services, and the mock services, and the Redis services that provides the database-related services. So for the Siemens scenario, they want to estimate which services will be the bottlenecks of the whole scenario. Like if the SLB GW is the bottleneck of the whole system, so they would like to add more resources to this service, and the bottleneck can be avoided to improve the whole system performance. Okay. So how to plan the resources for the whole system? From the service provider's perspective, identifying the bottlenecks at the early stage is not easy. The main reasons include it's not feasible to arrange testers to perform a large number of stress tests to evaluate all the scenarios or all the configurations. And secondly, it's not cost effective. And the third reason is the evaluation results may be not reproducible due to the uncontrolled factors, including the networks or the resource usage. So one feasible way is to use a simulation toolkit. With the simulation toolkit, the users can model the resource provisioning of various cloud infrastructure configurations, and they can also generate reproducible results. So the Siemens company contacted with us to use the CloudSim simulation toolkit to evaluate their scenario. The CloudSim simulation toolkit is a widely used cloud data centers toolkit, which can model and evaluate the different algorithms in cloud computing environment. So based on the agreement, we model the scenario of Siemens in Cloud Scene. So our objective is to generate various metrics to help plan resources for the user cases in Siemens scenarios. Our main contributions are as follows. We presented a framework to identify the potential bottlenecks for multiple services interacted in the cloud, such the service provider can optimize their resource planning. And we also proposed a policy gradient approach to model resource utilization and predict the system behaviors under different loads, like the overutilized scenario and the underutilized scenarios. We also utilized Cloud Scene components to set up specific underlying IaaS infrastructure model specifically MindSphere service model, which is the Siemens service. Okay, to address the resource bottleneck prediction problem, we propose a framework named IRBS, which stands for Identifying Resource Bottlenecks Solutions. There are several components included in this framework. The input controller component handles the input workloads, and the resource usage model component is the key component of this framework. It produces the resource pool containing the CPU pool and the bandwidth pool, and then it can simulate the real scenario to perform the distribution of the loads. And the data fitting model component supports to calculate the evaluation results. The queue processing model controls two different queues by monitoring the data resource usage model, which namely deferral queue and the processing queue. As for the multiple service interaction component, it manages the interactions and the collaborations between different services. Based on this framework, we modeled our problem based on the reinforcement learning approach. We defined the possible states and actions for our approach, including the amount of loads, the CPU capacity of processing loads, and the bandwidth capacity to process the workloads, and the CPU resource usage, bandwidth resource usage. So in our proposed approach, we want to model the capacity of the CPU and the bandwidth resource usage, which are corresponding to the number of requests coming into the whole system. We also define the actions which will dynamically configure the capacity of the CPU capacity as per the requests, the unit of requests. In our model, we also model the CPU utilization of the services, and the services with the highest utilization will be regarded as the bottleneck of the whole system. We also define the reward function, which is defined as the cumulative errors in all the time slots. As our objective function, we aim to reduce the errors between the predicted resource usage and the realistic resource usage. Here is the algorithm that we proposed, which is called the policy gradient-based reinforcement learning approach. There are 5 main steps of our proposed algorithm. Step 1, the algorithm will initialize the system parameters, including the system states and the actions, and some other parameters that will control the whole algorithm. Then step 2, the algorithm will find the reachable states and the possible actions of the states. After finding these states and actions, the algorithm will update the reward of the states based on the transition of the states and the reward that are obtained by changing the states. Step 4 stands for calculating the policy gradient function, which will guide the policy to achieve the best states in the whole system. And finally, the algorithm will decide the actions to achieve the optimized states. Okay. To achieve our objective, we extend the original version of the Clouding Toolkit. In the original version of the Clouding Toolkit, it already had some features to simulate the cloud data centers components. However, for our Siemens scenario, it doesn't support the admission control and it doesn't support the Alibaba capacity. And we also need to add our policy gradient based algorithm into Clouding to fulfill our objective. So based on these requirements, we made the extension of the Clouding Toolkit. Okay. So for the experimental settings, we want to address some questions as below, like which components will have the bottleneck, and in what capacity, in what CPU configuration or bandwidth configuration, the QPS will reach like 20,000 cores per second, and how much resources should be added to avoid bottleneck. There are two tables. These two tables show the realistic data derived from the Siemens data. For example, in case 1, under the load 1,500 requests per second, if the system is provided with like 9 VMs and 18 ports, and the ECS cores are like 8 cores, and the port cores are 3 cores, and the bandwidth is 315 megabits per second. So the service response time will be like 100 milliseconds. So based on this realistic data, we train our model to find the best way to find the optimized value of the CPU capacity corresponding to the number of requests coming into the system. Here are some results for the underutilized scenario. So under this scenario, there is no resource there is no service experiencing the bottleneck of the system. So based on these results, our proposed approach can fit the realistic data well, like for the gateway workloads and the different number of requests. Our proposed approach can achieve a very close data with the realistic data of the Siemens scenario. This also happens for the CPU usage and inbound and outbound traffic of the bandwidth and the QPS values. Okay, so for the second scenario, we want to evaluate like when the QPS is 20,000 cores per second, which service will be the bottleneck of the whole system. So based on the experiments, we found that when the QPS is 20,000 cores per second, so the gateway can be the bottleneck of the whole services and the CPU utilization will also be the bottleneck of the whole system based on the figure B. We also evaluate our proposal approach with some baselines, including regression-based algorithms and the meta-heuristic algorithm, which is particle swarm optimization-based approach. We also evaluate some metrics to show the errors of our proposed approach, including RMSE, MAPE, and R-square. So based on the experiments, our proposed approach can achieve the best values for these metrics, like for the R-square. Our proposed approach IRBS can achieve a value 0.988. Okay, as for the conclusions, in this work we propose a resource bottleneck identification approach. We simulate multiple services interaction scenarios for the Siemens commoning scenario. In our proposed approach, the approach can predict resources and service bottlenecks. We also propose a policy gradient-based approach that can control the system actions and decide the parameters the system should configure. And as for the future work, we would like to design and develop a prototype system with the proposed algorithm. So that's the end of this presentation. Thank you.